Hello, I'm John Schueth of the University of Nebraska at Omaha, and on behalf of my colleague down at Laytock, I'd like to give you an overview of our presentation, which is the search for the world's fastest sand dunes, in which we measured sand dune migration using a inclusive and accessible way through means of Google Earth historical imagery. Sand dune migration is a very serious risk in a lot of communities as they are encroaching on communities, farmland, infrastructure. One example of this is the Nouakchott, Mauritania sand dunes, with an image here showing the sand dunes getting closer to the community itself. And this has led to a lot of push recently to understand sand dune migration, but also there needs to be a way that the people of the community like Nouakchott could actually investigate sand dune migration on their own to determine local risks that may be more important to them. Sand dunes have been measured in a lot of different ways throughout time, including the use of satellite photos. Digital elevation models can tell us where sand dunes are in various times. Physical measurements in the picture I have here in the bottom left shows a person putting a stake in the ground right there and measuring the actual movement of the dune crest through time. And in general, these accompany meteorological measurements to compare things like the wind speed and other stuff that could be important to understanding where and how dunes move. Previous work has shown a lot of things such as the shape, size, and environment all affects dune migration rates. This image here from Gay 1999 showed that the fastest dunes, which as axes are inverted, so the fastest and smallest dunes are down here, but generally there's an increase in speed related to a decrease in overall dune size from the width of the dune. And this led us to thinking about how we could make these sorts of measurements, which until now have been really restricted to academia or other more hardcore research angles, and move that into a space where the general public could use something to help assess local dune migration risk. And the one thing that we settled on was the use of Google Earth historical imagery. So I'll play this little video that shows some of these dune movements on Google Earth historical images. And what you're seeing is that just by looking at historical satellite images in Google Earth, you can clearly tell how dunes are migrating, what direction they're migrating in, as well as the speed in which they are going in. So in this case, if somebody lived near these dunes that we show moving here, they could open up Google Earth, which is completely free as long as you have an internet connection, find their area of interest or their community or their farmland, zoom into that and scroll through the historical images to determine what the risk to their property, livelihood, or infrastructure is based off of observed dune migration. And this way, this allows something that is a little bit more accessible and inclusive to all people to be able to determine something important like dune migration risks. And so what we really wanted to do with this work is not just show clearly that you can see dunes moving on Google Earth, because that's pretty obvious, but what we wanted to do is to determine if that using Google Earth historical images would provide a similar sense of the more quantitative remote sensing and other methods in which people have already used to measure dune migration. But the hope is that doing this, what you're basically seeing here on the screen right now, would give comparable results to published methods, in which case then we could be more confident that when people are actually using these methods to assess local risk, that they are getting accurate results, that they can determine go from a more qualitative assessment of dune migration just by looking at maps to a more quantitative assessment of how fast the dunes are moving, exactly what direction they're moving in. And so that was our goal for this project. So from that, we actually compiled a database of Google Earth dunes that numbered around 117 or so dunes. And from that, we selected a subset of 24 dunes that we actually looked at and measured dune migration rates for. Of these, a small handful have published rates, so they allow us to compare directly to what's been published before. The others have we observed as having a very rapid migration, and it allows us to determine that ultimate question that we started out with, which is where are the world's fastest dunes located? And we went about this in a way that we wanted to standardize the way that we went about this, I should say. So what we did is we took each satellite image and subdivided it into a counting grid. In this case, this is supposed to standardize the way we count things, but also eliminates the need to count every single dune on an image, which can be very cumbersome and is not likely how the general public would approach dune migration on a historic or a satellite historical image, and like what we're working with. So the counting grid that you're seeing here, each of these cells is standardized with an area of 40,000 square meters. We did that on all of the images. All of the cells had 40,000 square meters. And then you can see the dunes in this field in the background on the left over here. And then every dune crest in the white that intersects the grid was marked with a dot in this image. You see there's some there and there and there. And we would measure then that movement through time from the left, the early time step, to the right, the later time step. We also measured dune size by the overall crest length, which is this dashed line there, and that shows some sense of the size of the dune to relate it back to previous studies, which show a relationship between size and migration. So we have our intersection of the grid there. We measured length. We find all other dune crests that intersect the grid, at least at some point. And then over here on the right, we then measure the displacement and angle of displacement of those dunes in order to determine some sense of velocity, of overall dune velocity. Now, some of these arrows are dashed, and those are dunes in which the movement was more ambiguous. It was harder to tell where those dunes actually move from one time step to the other. In this case, what we'll do is put more images in between the endpoints so you can see at a finer scale how the dunes are moving, or we'll just throw those out because I think it provides less bias to the study to throw out a measurement than it does to force one in on a dune that you're not necessarily sure how it moved through time. So that's the overall method that we chose to do. And then when we compare this to published results, that's what you're seeing here on this graph. Each one of these names here is a different dune field that had published migration velocities, and we're showing the maximum as the plus, the mean as the circle, and the minimum as the rectangle. And the orange color at the top of each one is what we measured, and the blue at the bottom is what was in the database, so a published database. So in this case, measured versus published. This should overall show that our use of Google Earth historical images matches almost exactly what's been published before, which is great and gives us the confidence then to use this sort of technique and Google Earth in order to assess dune migration in ways that other papers have done before in the past. One of the things that we wanted to do is to compare dune speed to their size, as other authors have done before. And so this is not showing all of the measurements, but it is showing the top 3 fastest dunes, which are the Bodele, the Nosy Bay and Troca dunes field, and the Sanglong dune field. So those are the 3 fastest, and the 3 slowest on average, which are the Aberfraw, the Kobuk Valley, and the St. Anthony dune fields. And each of these points then represents the dune crest length, which is a measure of the size of the dune on the x-axis, and the migration rate, how fast they're moving, on the y-axis. And some things can be pretty clearly seen in this graph. And the first, if I just highlight one of the dune fields, the Bodele one, do that quick. So I've now encircled all the Bodele in the dark green. We see that there is a clear relationship there that the smaller the dunes get, the faster they move. And this matches what's been published before. However, what is also interesting here is that if we compare dune fields together, there is not a clear relationship between size and speed. There can be very fast moving small dunes, and there can be very slow moving small dunes. However, there does seem to be some threshold, maybe around 200 to 400 meters in crest length, in which you can no longer get fast moving above 40 meters per year rates. And so there is still some overprint of size onto this, but what's interesting is that by doing a global comparison like we've done here, we might be able to eliminate the size bias in migration rate studies and focus then instead on more the environmental aspects and climate aspects that are controlling dune migration velocities. So let's talk about the world's fastest dunes, as that's what you're all here to listen about. And I'm going to show you our top 3. I mentioned before what those top three were. The first one is the Bodele Dunes of Chad. These are diatomite dunes in a dry lake bed. You can see the little flipping animation I have here between the two end members that were measured, showing these dunes move through time. And generally the fastest ones are the smaller Barchan dunes, especially at the bottom of the image. The maximum speed that was measured here was 73.2 meters per year. The next are the Nosy Van Androka National Park beach dunes in southern Madagascar. These are just this narrow dune field right along the beach, and I'm showing several flips of the images through there. And you can see it in the original notation of Google Earth that these were noted as being very fast, and in fact they are. I should also point out that this is interesting because you can see there's cloud cover in that last image, which does make measuring some of these dunes more difficult. So it's possible that this field had faster dunes that were covered up by the cloud cover and we failed to measure them. But the maximum speed here is 77 meters per year, which is pretty fast. But the world's fastest sand dunes that we measured belong to the Sanglangsha Dune field in China. See on the map where we are, kind of on the border between China and Mongolia. And this has an interesting set of a lot of larger Barchan dunes here mixed with these smaller ones. The arrows show actually the two fastest dunes that we measured in this field, and they could see just how quickly they're jumping through these time steps. The fastest measurement we saw here was 81.4 meters per year. And there is a paper published on this dune field where the authors of that paper noted a measurement of 90 meters per year, which is a lot faster than what we measured. Fortunately, the grid system we had missed that 90 meters per year, but it does fit in with the published record, which suggests that the world's fastest dunes are in this Sanglangsha dune field in China. So that's interesting. We found the world's fastest dunes, but the next question is then why maybe are they the fastest dunes? What makes them so special compared to other dune fields? And so we're going to show some correlations now with climate data. And the first set of climate data that I'll point out is wind power density. And this is a measure of the wind's ability to do work. So it's actually in watts per meter squared, the power per surface area. And this is because wind speed itself is not enough to move sand grains, and actual dune migration is related to grain size and things like that, which we can't measure on Google Earth. So instead we use this measurement of wind power density, which is derived from the Global Wind Atlas, which is a free open source website that provides wind sort of data. And their goal is to identify areas that would be prime targets for electrical power generation. And so wind power density for them is a measure of how much the power the wind has to turn an electrical turbine. We thought that this would be an adequate measure then of equivalent power of that same wind to push sand grains along a dune. And so we used that. And when we compare the maximum migration rates of the fastest dune speeds to wind power density, there is a moderate but yet statistically significant positive linear correlation between migration rate and wind power density, which isn't shocking. It fits in everything else that people have talked about before in the literature. The other thing we compared to is annual precipitation. And this is that data showing the max migration rate on the y-axis and annual precipitation from the UN's FAO website, which is a global assessment of water and water resources. And they have a great website. We can go and find out all sorts of things like annual precipitation for these different locations. And this one has a very weak and slightly statistically insignificant correlation between max migration and annual precipitation. But there is one problem with this, and that's this single data point up there, which are those Madagascar beach dunes of the southern coast of Madagascar. And that is a place where we have very rapid movement, but it's a lot wetter than what this linear model would suggest it should be. And what's interesting about that location, if we just take a look at it while I talk about it, is that it is next to a coast in a very wet region, but it's also very remote. It's probably one of the most remote sites that we have away from any sort of habitation or community. And so what the UN site does is they extrapolate and interpolate weather station data in order to build out their maps. And so what could be happening here is that you're so remote that we're not getting a very accurate readout of precipitation at the site. The other thing that is worth noting is that that UN website shows that this is a very seasonal wetness. And in fact, if they have a very dry season, in which case also that corresponds to also maximum wind speeds. And so it's very possible that what we're seeing at this site is that during the dry season, the dunes move very quickly and then they slow down or cease moving during the wet season. And if that's the case, we can actually go back to this plot and move that outlier because it could be a true outlier in the sense it's not telling us what the system is actually like. And if we do that, our correlation becomes stronger and statistically significant. In this case, what it's telling us then is that the more rain you have, the slower dunes move. Even in the case of a very fast moving dune system, the seasonal rains probably slow that dune system down. And so in the end, the world's fastest dunes tend to be in environments with very strong winds, not necessarily fast winds, but strong winds. That strength relates to things like environment or not altitude, the roughness of the terrain. Are there lots of hills and stuff blocking the winds, vegetation, things like that, but also very dry weather. This can either be dry seasonally or dry all year round. And so then there's really important implications for that when we think about future desertification, which is a problem the world is facing right now. A lot of the world is becoming drier and warmer as a result of anthropogenic climate change. And this is a map showing from the US Department of Agriculture the increased vulnerability of desertification in the red around the world. So a lot of these places that are on the fringes of these deserts where people might be worried about sand dune migration risks should end up being more worried, I think, because we're showing here that there's evidence that as the world dries out and warms up, we could start to see faster dune migration. But these are obviously initial results, and the main drive of this work was not necessarily to link dune migration concretely to environmental changes. That's something for future work, obviously, with a lot more data. But what's really showing is the power of using Google Earth, which is a free open access software, to assess at a quantitative level dune migration in ways that people up to this point have not really had access to. This then takes that power of understanding dunes and places it within the hands of the general public, which will help communities and people assess local risks. Thank you very much for listening to this presentation.